In this video, we will be talking about gathering and organizing data. Our learning objectives are to define data and statistics, to explain the difference between a population and a sample, to describe 4 basic methods of sampling, to contrast descriptive and inferential statistics, and to construct a frequency distribution for a data set. And then finally, we will learn how to draw a stem and leaf plot for a data set. So let's get started. One of the big issues being discussed over the last 20 years or so in higher education is grade inflation. The perception that college students in general are getting much higher grades than they used to. But perception and reality are often two different things. So how could we decide if this is actually taking place? And if so, what are some possible reasons? Are students just getting smarter? Are professors lowering their standards? In order to examine questions like this, it would be very valuable to gather some data. So let's define this term. Data are measurements or observations that are gathered for an event under study. Once data have been collected, in order to get anything of value from them, the data need to be organized, summarized, and presented in a form that allows observers to draw conclusions. This is what the study of statistics is all about. Statistics is the branch of mathematics that involves collecting, organizing, summarizing, and presenting data and drawing general conclusions from the data. So let's get started here with some important concepts, starting with the idea of populations and samples. In the case of grade inflation, relevant data might be average grade point averages for students in several different years. This table 11.1, shows some GPA data from the website gradeinflation.com. So in this table, we have 2 columns. The first column is a year, right? We have several years. And then over here, we have average undergraduate GPA for each year. Okay. The numbers here certainly appear to indicate that grade inflation is real. But where did the data come from? Were grades from all colleges included or just some of them? When statistical studies are performed, we usually begin by identifying the population for the study. A population consists of all subjects under study. In our example, the population is all colleges in the United States. If you are only interested in study habits of the students at your school, the population would be all of the students at the school. More often than not, it's not realistic to gather data from every member of a population. In that case, a smaller representative group of the population would be selected. This is called a sample. A sample is a representative subgroup or subset of a population. The GPA data in Table 11-1 were gathered from a sample of 75 schools. The reason the data are compelling is that the sample is representative. Representative of the population as a whole. The schools chosen vary in size, cost, and geographic location. Some are public and some are private. In order to ensure that a sample is representative, researchers use a variety of methods. Let's go over now some of the most common methods for obtaining a sample. Sampling methods. So in this section, we will study 4 basic sampling methods that can be used to obtain a representative sample. We will look at random, systematic, stratified, and cluster sampling. So let's look at each of these in turn. First of all, we'll look at random sampling. In order to obtain a random sample, each subject of the population must have an equal chance of being selected. The best way to obtain a random sample is to use a list of random numbers. Random numbers can be obtained from a table or from a computer or calculator. Subjects in the population are numbered, and then they are selected by using the corresponding random numbers. This allows for an unbiased sampling method where every subject of the population indeed has an equal chance of being selected to be included in the sample. A systematic sample is taken by numbering each member of the population and then selecting every kth member, where k is a natural number. For example, the researcher from gradeinflation.com might have numbered all of the colleges willing to release grade information and chosen every 10th one. When using systematic sampling, it's important that the starting number is selected at random. When a population is divided into groups where the members of each group have similar characteristics, this could be like large public schools, large private schools, small public schools, and small private schools, and members from each group are chosen at random, the result is called a stratified sample. The purpose of a stratified sample is to ensure that all groups will be properly represented. When an existing group of subjects that represent the population is used for a sample, it is called a cluster sample. For example, an inspector may select at random 1 carton of calculators from a large shipment and examine each one to determine how many are defective. The group in this carton represents a cluster. In this case, the researcher assumes that the calculators in the carton represent the population of all calculators manufactured by the company. Samples are used in the majority of statistical studies, and if they are selected properly, the results of a study can be generalized to the population. Let's look at an example. Choosing a sample. A student in an education class is given an assignment to find out how late typical students at his campus stay up to study. He considered 4 different methods for gathering data. Describe what type of sampling method he's using in each case, and then describe whether you think he's likely to get a representative sample. Let's take each of these one by one. For A, stop by the Union before his 9 a.m. class and ask everyone sitting at a table how late they were up studying the night before. Okay, this would be an example of a cluster sample. And that is because he is choosing all students in a particular place at a particular time. Okay, say all students in particular place at particular time. Okay. Since he's polling people, so it's the cluster sample. Let's talk about the representative. Would we be likely to get a representative sample in this case? Well, since he's polling people early in the morning, Those that tend to stay up very late studying are less likely to be included in the sample. Right? Would you be at the Union at 8:30 in the morning if you were up until 4 a.m. studying, right? Probably not. So in this case, the sample that you get is probably not representative. And that's probably largely because of the time of day that the sampling process took place. Okay, for B. Ask the school registrar to give him a list of 50 students whose student ID numbers end in 4. So this is an example of a random sample. Okay. Generally, we would think that the last digit of an ID number is likely to be completely random. How representative it is might depend on how big the campus is. If there are like 500 students on the campus, this would probably be pretty good. If there are 50,000, maybe a little bit less so. But in general, this is probably decent. You might say it's give us a sample that's probably mostly representative. Okay. C. Survey the 5 people sitting closest to the door in each of his 5 classes. This would be an example of a stratified sample. Okay. And the stratified sample, since he's randomly picking subjects from existing groups, which would be the classes. As far as whether it's representative, this seems like it's probably a decent approach, depending on what kinds of classes he's taking. If he's surveying students from all senior level courses that require a lot of studying, that might bias the results toward people staying up later. So this would be more likely to give a representative sample if he surveys students from a variety of different classes, right? So if they're, it would be less representative if they were all like senior level classes, maybe a little bit more representative if they were all lower level classes. But in general, we might say this would give us a mostly representative sample. Okay. D. Look at the campus directory and choose the first name at the top of each page. This is an example of a systematic sample. Okay. And this is a good method for getting a sample that would be representative. So yeah, I'd say this would probably give us a representative sample. Pretty likely to give us a good representative sample. Okay, let's move on now and talk a little bit about the difference between descriptive and inferential statistics. There are 2 main branches of statistics: descriptive and inferential. Statistical techniques used to describe data are called descriptive statistics. This is based on collecting, organizing, and reporting data without using the data to draw any wide-ranging conclusions. For example, a researcher might be interested in the average age of full-time students on your campus and how many credit hours they're scheduled for this term. In that case, they could gather that information for every student in which case the averages would be describing a definite situation. Descriptive statistics often involves gathering information about every individual in a population. Statistical techniques used to make inferences are called inferential statistics. This is based on studying characteristics of a sample within a larger population and using them to draw conclusions about the entire population. For example, the Bureau of Labor Statistics estimates the number of people in the United States that are unemployed every month. There's just no way they can survey every person in the workforce every month. So the Bureau picks a sample of adults to see what percentage is unemployed. Then they use that information to estimate the unemployment rate for the entire population. As we study statistics in this chapter, from time to time we'll think about the distinction between descriptive and inferential statistics. Are we describing data that have been gathered, or are we using data to draw conclusions or to make predictions? That's an important distinction to keep in mind. Let's turn our attention now and talk about frequency distributions. The data collected for a statistical study are called raw data. In order to describe situations and draw conclusions, we need to organize the data in a meaningful way. Two methods that we will use are frequency distributions and stem and leaf plots. There are two types of frequency distributions: the categorical frequency distribution and the grouped frequency distribution. A categorical frequency distribution running out of space here, sorry. A categorical frequency distribution is used when the data are categorical rather than numerical. Example 2 shows how to construct a categorical frequency distribution. Let's go over this. So let's say 25 volunteers for a medical research study were given a blood test to obtain their blood types. The data follows. Let's construct a frequency distribution for this data. To make our frequency distribution, let's do it down here, we need to start by making a table shown with all the categories represented. So we're going to have a column in our table, which we will label type. And there are 4 blood types: type A, type B, type O, and type AB. Okay. The second column is mostly used as kind of a helpful tool to help us figure out the frequencies for each category. So we're going to put a column here which we call tally. Okay. And then we'll do a third column, which we will call frequency. Okay. So our goal in the frequency column is to figure out how many of the volunteers were type A, how many were type B, how many were type O, and how many were type AB. Tallying these values can help us figure that out. So what we'll do is we will kind of go through and let's start with A, right? So every time, we'll go row by row. Every time we see an A, I'm going to cross it out and put a tally. Go down here, there's the next one, cross it out, put a tally, and then cross it out, put a tally, cross it out, put a tally, cross it out, and then tally. So that would be a frequency of 5, which we'll put that in the frequency column there. Okay. And then we do move on to B, right? So cross it out, tally, cross it out, tally, cross it out, tally, cross it out, tally. Let's see, cross it out, tally, cross it out, tally, cross it out, tally. That looks like that has a frequency of 7. Okay. Moving on to O. Let's go again, going row by row. Cross it out and tally. Cross it out, 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 tally. That looks like that's a frequency of 9. Okay. Now all that's left is the ABs. So let's go row by row and figure out that frequency. Cross it out, tally, cross it out, tally, cross it out, tally, cross it out, tally. Looks like that's a frequency of 4. Okay, so there is my frequency distribution, specifically my categorical frequency distribution. Okay, another type of frequency distribution that can be constructed uses numerical data and is called a grouped frequency distribution. In a grouped frequency distribution, the numerical data are divided into classes. For example, if you gathered data on the weights of people in your class, there's a decent chance that no two people have the exact same weight. So it would be reasonable to group people into weight ranges, like 100 to 119 pounds, 120 to 139 pounds, and so forth. In the 100 to 119 pound class, we call 100 the lower limit and 119 the upper limit. When deciding on classes, here are some useful guidelines. 1. Try to keep the number of classes between 5 and 15. We wouldn't want weight classes like 120 to 122 pounds. The result would be so many classes we wouldn't be much better off than if we used individual weights. 2. Make sure the classes don't overlap. Notice that we didn't choose 110 to 120, 120 to 130, and so on. That would put someone that weighs 120 pounds into 2 different classes. 3. Don't leave out any numbers between the lowest and highest, even if nothing falls into a particular class. Even if nobody weighs between 160 and 169 pounds, we still want a class for that because it may be useful to know that nobody is in that range. 4. Make sure that the range of numbers included in a class is the same for each one. We wouldn't want the first class to go from 100 to 120 pounds and the second to go from 121 to 130 pounds, for example. Okay. And then 5, the beginning and ending values have to be chosen based on how the data values are rounded. If our first 2 classes are 100 to 119 and 120 to 139, where would someone who weighs 119.6 pounds go? If you said nowhere, you win. If any of the weights in our data set are rounded to the nearest tenth, we'd want to make our classes things like 100 to 119.9, 120 to 139.9, and so on. Okay. So now that we've kind of gone over these guidelines, let's do an example. So here's our example. We have this table here. The data in this table represent the record high temperature for each of the 50 states in degrees Fahrenheit. Let's construct a grouped frequency distribution for this data. Okay, so to get started, we want to kind of do a little bit of work to set this up with a reasonable number of classes. So let's do this. Let's start by finding the highest value and the lowest value. If I scan through this, it looks like the highest value is going to be 134, corresponding to California. The lowest value looks like is probably 100, corresponding to Alaska. So I'm going to subtract the lowest value from the highest value. So that gives me 134 minus 100, which equals 34. Then we want to kind of think about what range we want for each class. And again, there's more than one good answer to this, but a range of 5 degrees kind of seems reasonable to me, right? Having each interval or each class covering a range of 5 degrees. So maybe we'll just kind of use that and move forward with that. Okay, so what we can do, if we all right, so if we're using a range of 5 degrees, so what we would do is we would start with the lowest value, which is 100, okay? And let's do this. So we're going to do a column, which we will call class. Yeah, okay. Sorry, before I do that, let's just take this this number we calculated right here, the 34, right? We were saying we want maybe a range of 5 degrees for each class. If I take this total spread and divide that by kind of the range we're thinking of, that works out to be 6.8, which basically tells me that if I am using a range of 5 degrees for each class, I'm going to need 7 classes because the 6.8 rounds to 7, right? So I'm going to need 7 classes to cover the spread of all the data. And again, that seems pretty reasonable. 7 classes is pretty good. If you chose a range of 4 degrees, that's not bad either. That would probably result in about 9 classes. But let's stick with this range of 5 degrees for each class. So what we're going to do is we're going to set up a table. In the first column, I will label class. And once again, we'll do this tally, because this is just a useful tool for helping us find the frequencies. And then we'll do frequency. Okay, so to fill in the classes, we will start with the lowest value. And we said the lowest value in the entire data set was the value corresponding to Alaska, which is 100. Okay, put that here. And then, since we want a spread of 5, what we're going to do is we're going to add 5, and that will give me the next lower class limit. Okay, so the next lower class limit will be 105. Okay, and then the next lower class limit will be 110. Okay, and so on. Now we said we would need a total of 7 classes. So let's keep going till we have 7 lower class limits. Okay, so the next one would be 115, that's 4, and then 120, that's 5, 125, that's 6, 130, and then 135. Sorry, did I do that right? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay, so, yeah, okay, so I think we can just back off one here. Yeah, we don't actually need that one, okay? Because we only need 7 classes. Okay, so now we got to fill in the upper class limits. The first class is going to go up to 104. Why 104? Well, because it has to stop just before the beginning of the second class, right? And furthermore, we can't have any gaps between them. So if the second class starts at 105, the first one needs to stop at 104. And furthermore, our class limits need to all be whole numbers because all the numbers in my table are whole numbers. Okay. So that tells me that class 2 will go up to 109. Okay. And then the third class will go up to 114. And then we've got 119 here, 124 here, 129 here. And the last one, using the same pattern, notice that if I take each of the upper class limits and add the class range, which is 5, to each successive upper class limit, right? 104 plus 5 is 109, plus 5 is 114, plus 5 is 119. So that means the upper class limit of the last class will be 129 plus 5, which is 134. Okay, now we fill in the frequencies. Okay, so my first one is 100 to 104. So I'm going to go through, and let's just go through them alphabetically. I'm going to look for all the numbers that fall within this range from 100 to 104. And every time I find one, I'll put a tally. So the first one I see is Alaska, right? So, and I'll cross it off when I see it and then put a tally. Between 100 and 104. The next one looks like it's Hawaii. So tally. Okay. 100 and 104. Kind of going through these. Oh, I see Rhode Island. There's another one. Okay. And looks like that's it. So frequency of 3. Then 105 to 109, right? So we do the same thing. Every time we see one, we cross it off and put a tally. 105 to 109. Okay, so I see Connecticut. There's one. Florida. 2. Okay. Maine. Maryland. Okay. Massachusetts. What else do we have here? New Hampshire. Um, 105 to 109, New York. Okay, what else do we have here? Vermont. And that looks like that's it. So 5, 6, 7, 8. You know what? I'm going to actually adjust this because I'm going to need more room for my tallies. So just move this over to give myself more space. So this first one was 3. Second one was 5, 6, 7, 8. Okay. The next one is 110 to 114. So 110 to 114. I've got Alabama. There's 1. Delaware. There's 2. Georgia, 110 to 114. Kentucky, Louisiana, Michigan, Minnesota, 110 to 114. New Jersey, okay. North Carolina, Ohio, Pennsylvania, oops, sorry, South Carolina, Tennessee, Virginia, West Virginia, and looks like Wisconsin. Bunch of them in that category. So 5, 10, 15, 16. Right there. All right, then we got 115 to 119. 115 to 119. Colorado. This is going to be, okay. Idaho. Illinois. Indiana. Iowa. Okay. 115 to 119. So Mississippi, Missouri, Montana, Nebraska. Okay. What else do we got? Oregon. Okay. And looks like Utah. Washington. Wyoming. Is that it? 5, 10, 13. Looks like that's 13 there. Okay. 120 to 124. There's not that many left, right? So the rest should go fairly quickly, but we have Arkansas. And then 120, 124, nothing there. Kansas. Nothing else there. New Mexico. North Dakota. Oklahoma. Okay. South Dakota. And Texas. And that looks like that's it for that category. That's a frequency of 7. Okay. 125 to 129. Now we're getting to some really high temperatures. Let's see. We got Arizona. So there's 1. Okay. And what else? Looks like Nevada. Okay. And everything else is crossed off, so it looks like just 2 there. And then 130 to 134, there's only 1 left. That's California. So only 1 in that category. Okay, so there is my frequency distribution, right? Again, by using a class range of 5 degrees. This is what this would look like. Okay, let's move on and talk about the next way to an alternate way or another way to organize data. And this is to use what we call a stem and leaf plot. Stem and leaf plot. Sometimes just called a stem plot. For this type of plot, each data value or number is separated into 2 parts. For a 2-digit number such as 53, the tens digit 5 is called sorry, my line got really shortened, but it's called the stem. And the ones digit, the 3, is called its leaf. Okay. For a 3-digit number, say 138, the first 2 digits, the 13, are used as the stem, and the third digit, 8, is used as the leaf. For values rounded to the 10th place, like 8.4, you can use the value to the left of the decimal place as the stem, and the 10th place to the right of the decimal place as the leaf, as in our next example. In any case, the very last digit is used as the leaf, and what comes before is the stem. Note that we will include a key with our plot that clarifies what the stems and leaves represent. So here's our data for our next example. The following data are the percentage of adults that had been fully vaccinated against COVID-19 as of July 1, 2021. Draw a stem and leaf plot illustrating this data. Okay. So to do the stem and leaf plot, what we do is we notice that the data values range from, what do we got? A low of, it's like 30, to a high of, quick scan through the data here. Looks like the highest is Vermont here at 66. So I'm going to, that means my stems, the stems are always the first digit, right? So my stems will be 3s, 4s, 5s, and 6s. So for my stem and leaf plot, I'm going to do a column which I will label stems. My stems are the numbers 3, 4, 5, and 6. I'm going to do this, then I'm going to put over here another column which I will call leaves. Okay. Now we go through the data values one by one, writing the appropriate leaf next to the matching stem. Right, so yeah, so let's just go through the data one by one. And all right, so let's just go column by column, right? So Massachusetts, right? It has a stem of 6 and a leaf of 2. So I'm going to put the leaf right here, okay? Maybe I'll cross it off as I go, just so I know I've covered that one. Michigan, right, has a stem of 4, a leaf of 7. So we'll do that. Minnesota, 52. Okay, we'll put a 2 there. Mississippi, 30. So we'll put a 0 right there, okay? Missouri is 39. So what I do now is I put the 9 just to the right of the 0, right? Because now I have a second data value with the same stem, right? So I just line up the stems horizontally here. Montana is 43. I'll put a 3 right there. Nebraska is 48. Put an 8 right there. Nevada is 42. Put a 2 right there. Okay. New Hampshire is 56. So I'll put a 6 right there. New Jersey is 55. Put a 5 right there. New Mexico is 55. Put a 5 right there. New York State is 54. Put a 4 right there. North Carolina is 42. Go back to my my stem of 4 and put a 2 right there. 39. Put a 9 there. Ohio is 45. Oklahoma is 38. Oregon is 54. Pennsylvania is 50. Rhode Island is 59. Oh, shoot. Okay. Rhode Island is 59. Okay, got that. And then South Carolina is 39. South Dakota is 45. Tennessee is 35. Texas is 41. Utah is 37. Vermont is 66. Virginia is 52. Washington is 55. West Virginia is 37. Wisconsin is 50. Wyoming is 35. Okay. I get that right. So, all right. Last step isn't strictly necessary, but many folks prefer stem and leaf plots with the data in order, in numerical order, right? So if I do that, the stems remain the same, 3, 4, 5, 6, but I arrange the leaves in numerical order, right? So the first one, I would have a 0, and then it looks like, did I miss a couple here? 35, I got 35. I don't know. If I arrange them in order, I've got 0 and then 5, 5, 7, 7, 8, and then I've got 3 9s, 9, 9, 9, okay. For the 4s, down here I've got, 1, and then 2, 2, and then a 3, and then looks like 2 5s, okay, and then a 7 and an 8, okay. And then the 5s, this is the longest one, right? I've got 2 0s. I don't have any 1s. I've got 2 2s, right? And then no 3s. I've got 1 2 4s. I've got 1 2 3 5s. Okay, 1 6. No 7s, no 8s. Looks like 1 9, right? So we've got that. And then 2 and 6 for the last one, right? So again, that's just kind of generally considered good practice, is to rearrange the leaves in numerical order, although it may not be strictly necessary. So that's what a stem and leaf plot looks like, right? It's just a nice way to kind of summarize data in a fairly quick and simple way with a little table format. So that's it for this video. So we'll wrap this up here. Thank you for watching.